So we're continuing the series today, 2013 USNCO Locals 31 through 40. So starting with 31, we have to write an equilibrium expression. Capital K is the equilibrium constant, and we're writing an equilibrium expression, which is a quotient, right? So we have the activities of the products over the activities of the reactants, and the activity is kind of a complex topic to examine fully. But basically, a pure solid has an activity of 1, and a pure liquid has an activity of 1. And since we're doing division, either multiplying or dividing by 1 has absolutely no meaning whatsoever, so that basically means that you completely disregard solids and liquids in the equation, and you're just left with this O2 to worry about. It's on the product side, so we know it goes in the numerator, and from looking at our answer choices, it looks like they want Kc, C for concentration, rather than Kp. P would mean that we're looking at partial pressures. So we've only got one O2. So O2, you can put the 1 in the denominator to just symbolize that there's nothing there. The reason we're not bringing O2 up to any power is because its coefficient is 1. If its coefficient was 2, like the liquid mercury, then we would square it. I'm not going to square it because I'm going to forget to erase that, but essentially the coefficient is related to the coefficient. Did I really just say that? Okay, the coefficient is related to the exponent. Number 32. Okay, so it's a Le Chatelier's principle problem, and you're basically just trying to shift equilibrium to the right because NO2 is on the right. Let's look at what increasing temperature does. We're given that this is an exothermic reaction, so we can treat heat as a product because we know that in exothermic reactions heat is released. So increasing temperature is basically, if you want to think about it this way, it's like increasing the concentration, if you will, of heat. So since this goes up, we must shift left to compensate. So that's actually going to decrease the quantity of NO2 in the mixture, so not what we're looking for. Adding neon gas. So whenever you add some kind of noble gas, they're basically telling you to assume that no reaction occurs because noble gases are famous for their stability and stubbornness of not wanting to react. So if you add this, you're not changing the concentrations of anything within the container, so the equilibrium is not going to shift at all. H2O gas. Once again, that's a product, so we're going to do the same thing as when we increase temperature. Product goes up, we shift left. So, not good. Decreasing container volume. Okay, so we have 11 moles of gas on the right and 10 moles of gas. 11 moles of gas on the left, 10 moles of gas on the right. So we have more gas on the left. And whenever you're considering volume or pressure in Le Chatelier principle problems, there's a certain relationship. So if you increase the volume of the container, the reaction will switch equilibrium, it will shift in order to favor the side that has more moles of gas, because it can afford it because it has more space, right? So on the other hand, if you decrease volume, the reaction shifts to the side with less moles of gas. Looking at pressure, we know that PV are inversely related. So increasing P means that the reaction will favor the side with less moles of gas, and decreasing P favors the side with more moles of gas. So that's why B is our correct answer, because we shift to right because there's less moles of gas. 33, you really just need to know what your strong acids are. 2 is a strong acid, so that's why you wouldn't choose it. 34, conjugate base of bicarbonate. If you want to just visualize it, take the H off of HCO3 minus. H has a +1 charge, so essentially you're just left with the carbonate 2 minus ion. 35, saturated solution. Okay, so we're dealing with molar solubilities in KSP. One thing you can eliminate right away is Ag2S, because Essentially, KSP is related to molar solubility by a couple of discrete combinations. So if we look here, we have one cation, one anion, so molar solubility squared is equal to KSP, because that's just 1s times 1s. Here we have two cations times one anion, so two cations times one anion, so 4s cubed is equal to KSP. Here we have three cations, one anion. If you guys aren't seeing, this is 3 by the way, if you aren't seeing the pattern, basically, this coefficient is both the coefficient and the power. So 27s to the fourth is equal to KSP in this case, and we have two cations and one anion again, just like we had in B, so 4s cubed. And the higher your molar solubility is, the higher your concentration of Ag plus is going to be, and this just has a blatantly lower KSP than B, and they're both 4s cubed, so it can't be Ag2s. So we just have to explore A, B, and C. So if we solve for S in the equation here, let me do that real quick. I think we get like something on the order of 10 to the negative 6 or 5th maybe. 10 to the negative 5th. Okay, 1.3 times 10 to the negative 5th. So that's for A. If we look at B, we get S equals 6.5 times 10 to the negative 4th. If we look at C, we get S equals 1.6 times 10 to the negative 5th. So obviously B wins out because it's the largest. 36. Okay, so we're pretty much doing the opposite process that we just did in 35. So we have 1, 2, 3, 4, 5, 4, 4. We have this many moles of manganese 2 carbonate in solution. And let me see how many moles that is. I think that's 4.73 times 10 to the negative 7th moles. But we have to be careful here because we're finding KSP, and KSP is found by multiplying concentrations together, and we don't have a concentration yet. So we need to divide this value by 0.1 liters. And the reason we chose that value is because it just blatantly tells us that we have that many. Yeah, so then your concentration will be 4.73 times 10 to the negative 6. And you would just square that because, like we were exploring before, one cation, one anion. So your expression is actually really simple. And if you square it, your KSP is equal to 2.2 times 10 to the negative 11th. Okay, 3 metals, ABC, Voltaic cell. Okay, voltaic or galvanic cell means that the reaction itself is spontaneous and it's not battery powered, but instead it's generating power by itself. A is the cathode, C is the cathode, A is the anode. Okay, so how we can interpret this? We know that reduction happens at the cathode and oxidation happens at the anode. So if A and B are in solution together and A is at the cathode, so that means A N plus, because we don't know what metal this is, but like the A something plus anion or cation is getting reduced to the A metal. So that means that its reduction, the reduction of A's metal ion, is more favorable than the reduction of B's cation. I think I kept saying anion. Sorry. Yeah, so the reduction potential of A is greater than the reduction potential of B. So anything that says otherwise, we have to get rid of, so that's B and D. We look at B and C. Same logic, the reduction potential of C must be greater than the reduction potential of B, so that gets rid of our other answer choice. Just to go through it, this means that the reduction potential of C must be greater than the reduction potential of A, because A is more likely to get oxidized. Okay, 38, same oxidation state. Okay, so this kind of has to do with redox chemistry. Here we have an overall charge of 1, only nitrogen, so oxidation state has to be 0. Here, -2 and +1, because once again you have to balance to an overall charge of 0, and you want to assign priorities. Oxygen is almost always at a -2, and nitrogen can vary, so you want to assign an oxidation state to oxygen first, and then move on. So here, 0 clearly does not equal 1, so it's not C. Here, same logic. So here we went from oxygen to hydrogen to nitrogen. Yeah, I think that's the correct way to do it. You might want to go to hydrogen first, but either way, it's a pretty like definite answer. Like you know what you're gonna get. So 2 does not equal 3, so that's not it. We just did this one. I don't know why I'm doing the work again. And pretty sure it's 5. Yeah. 3 does not equal 5, so A must be our answer. Like we established before, it's 5, and it's also 5 here because it's -2. Okay, 39. What is the oxidizing agent? Okay, so don't be fooled. It cannot be anything on the product side, because oxidizing and reducing agents, they've got to be reactants. If you've learned this before, the oxidizing agent makes something else oxidize, so that means it has to be reduced. So we're looking for something that's getting reduced. Let's consider lead metal, for instance, like just the element. It's got an oxidation state of 0, as it is right here, because it's literally by itself, and it has overall charge of 0. It goes from 0 to +2. That's an increase in charge. So you're losing electrons, that's not getting reduced. So it's obviously not this. H plus just goes from +1 to +1. Nothing's happening to it. HSO4 minus. The SO4 actually stays intact, so once again, nothing's happening to it. So we're left with PbO2 to choose. Okay, number 40, we've got a voltaic cell. Once again, that's a galvanic cell. The reaction itself is spontaneous. It's not battery powered. Okay, so it tells us that we have 1 molar concentration solution, so that means we're dealing with standard concentrations and conditions here, like it tells us here too. And we're given the standard E overall. And we're also given this half reaction value. We know that Cu2 plus is getting reduced. I mean, I guess it could be Cu plus, but that's not really what's important right now. We know that a copper cation is getting reduced because it tells us that Cu is the cathode. So we have to figure out what's getting oxidized. So if we do this, U cell, or E overall, however you choose to write it, is equal to E reduction 1 minus E reduction 2. The reason it's a minus is because you have a reduction plus an oxidation, and for this second reaction, oxidation and reduction are essentially opposite steps, so that's why you flip the sign. So let's see, 0.47 equals 0.34 minus this value, and that value turns out to be -0.13. Alright, tune in next time for 41 through 50, and subscribe if you want to see more.